So here we have the last video of this numerical, guys. I'm really very sorry to create such a different parts, but I cannot make the video more than 30 minutes. Okay, that's what limit I have, because I cannot speak in a continuous straight proper way. So I make this video in 4 parts. So now this is what the last step for the check for the shear stresses at a junction of steam and base slab. Also at the end of this numerical, I just show you the what is the reinforcement detail of the retaining wall for this numerical. I hope that you will get properly all problem. So now here is what we need to do for what is the first step we need to do in this check for shear stresses at junction of steam and base slab. First is what you need to determine what is the net working shear force you need to calculate. What is the net working shear force? Okay, so if you wanted to calculate the net working shear force, which is given by capital V, which is nothing but the 1.5 of P minus dW, where 1.5 multiplied by P is nothing but the value 81.12, okay, minus the W is nothing but 102.4. Now the P and W, where I get the P is nothing but which is I get from the which is nothing but a total horizontal earth pressure. If you wanted to see all this value, you can just take my the next last second last video. Okay, so here we can get what is P is nothing but we can say as it is nothing but the total horizontal earth pressure. Okay, and W is nothing but the maximum possible friction forces. Maximum possible friction forces. Okay, so now after that you need to just get the answer of this equation, which is nothing but 19.28 kilonewton. Okay, after that, after getting the net working shear force, you need to calculate what is the factored shear force. Okay, factored shear force, okay, which is nothing but 1.5 multiplied by V, which is nothing but 19.28 multiplied by 1.5. So that is this value multiplied by 1.5. So you get the answer, which is nothing but 28.92 kilonewton. Okay, now after that, after getting all this value, you need to calculate the third value, which is nothing but called as the tau v, which is nominal shear stress. After that, the nominal shear force, which is tau v, is nothing but 28.92 multiplied by 10 raised to power 3 divided by 1000 multiplied by 400. Okay, so we get the tau v, which is nothing but 0.072 Newton per mm square. Okay, after that there is one equation which is nothing but, if you, I think everyone is everybody aware about this equation, 100 AST upon B into D is equals to, okay, 100, what is AST? We have the total AST for steam, okay, which is 1000 multiplied by 400. You get all the value from my previous videos. Okay, don't worry about this. Okay, so it is 1.25. Now with respect to this value and with respect to this value, from table number 19, okay, IS 456 2000, with the permissible shear stresses. Okay, the permissible shear stresses. Okay, the permissible stresses, which is nothing but tau c, by interpolation formula we get it as 0.40 Newton per mm square, and this tau c value is greater than, okay, tau c value is greater than tau of v, that means this value 0.72. Okay, so this means the with the tau c, that means the permissible stresses is greater than the nominal shear stress, that means the your shear stresses are within the safe limit. Okay, so safe shear. So now I'm going to give some brief about the reinforcement detailing of the retaining wall. You can see over here, guys, this is what the retaining wall exactly what we designed in the all the numerical. Okay, now here in the retaining designing, there is what steam, shear key, base slab, toe slab, all these things we design, okay, properly. So you need to watch my each and every video of the cantilever retaining wall from the part 1 to the last part. Okay, I'm sorry to make the all such a different types of the parts, but it is important. Now coming toward the diagrammatical representation of the reinforcement detail in the retaining wall, here you can see that this is what called as steam, this is called as a toe slab, and this is in a heel slab, this is shear key. Now what I designed, in what amount of the steel reinforcement we calculated in the design of steel, design of slab, heel slab, toe slab, and shear key, all the data we place here. Okay, you can see that this is what the 16 mm bar of 300 mm center to center of the distribution steel, main steel we place over here. Okay, this is what the bar of the 12 mm 200 mm dia, okay, we are placed over here. This is what the 200 mm top height. Okay, then these are the what main bar, distribution bar of the 16 mm into 150 mm center to center distance. Okay, then you can see in heel slab also there is a what is the dimension 450 1.55 is the total dimension. This is what 12 diameter 200 mm center to center distance bar we provided over here. Okay, now here it is what cantilever wall slab, what it is exactly we call the steam. Okay, now you can see over the longitudinal section. Okay, like 16 mm bar, these are what the vertical bar you are seeing over that is it, which is a 16 mm bar of 150 mm dimension. Okay, and 12 mm bar 200 mm dimension, which is this representation of the slab over here. Okay, this is what representation of the slab. This is very simple, you can just watch it out. Okay, very simple, there is nothing to do worry about the retaining wall. Okay, now you can see the 12 meter of the bar 200, which is this circle you are just seeing over here. These are what the bar, which is 12 mm bar to 200 mm center to center distribution bar, which is the like this manner place, and 16 mm bar 300 mm center to center, which is a vertical all over the kind of cantilever retaining slab. Okay, so all this is what all these what the reinforcement detailing I just placed for you from one book. Okay, so now I think, guys, I'm done with this numerical now, and if it is possible for you to please subscribe my channel, don't forget to like my video, and if you want any video, then please comment me. I'll be working on that video, and as soon as possible I'll upload it. Thank you and have a nice day. Bye bye.